The Diels-Alder reaction is a Nobel Prize-winning one-step 4+2 cycloaddition between a conjugated diene and a substituted alkene, dienophile, that forms a substituted cyclohexene ring. It is a concerted, stereospecific process that simultaneously creates two new carbon-carbon bonds, making it crucial for synthesizing complex six-membered rings. Diels-Alder reactions are among the most efficient methods for the total synthesis of natural products, particularly because many natural compounds contain polycyclic structures. In 1928, Otto Diels and Kurt Alder developed an extraordinary method for DNA synthesis, named the Diels-Alder reaction. A conjugated diene and a dienophile are involved in this reaction, which is a through 4+2 cycloaddition reaction that forms a six-membered ring having up to 4 stereogenic centers. Since it follows a concerted reaction path, the Diels-Alder reaction affords high stereospecificity. The stereochemistry of the product, formed by cycloaddition reaction between electron-rich 4pi and electron-poor 2pi systems, was explained by frontier molecular orbital theory. In the case of a thermally allowed Diels-Alder reaction between 1,3-butadiene derivatives and ethylene, there are both primary and secondary interactions. The secondary interaction produced a kinetic endoproduct in a greater amount than the thermodynamically stable exoproduct. Generally, the Diels-Alder reactions were done under thermal conditions, but were accelerated by using Lewis acid catalysis. Moreover, scientists reported that the Diels-Alder reaction can proceed at room temperature in quantitative yield by making the diene more electron-rich, or the dienophile more electron-deficient. Mechanism of Diels-Alder reaction. The Diels-Alder reaction is a two-component reaction, a 4-electron component, conjugated diene, and a 2-electron component, dienophile, often an alkene or alkyne. It is a concerted reaction, happens in a single step, involving a cyclic transition state. The reaction is highly stereospecific, retaining the stereochemistry of the reactants, with the endoproduct usually favored over the exo. The DNA must be in an SCS conformation to react. It is often accelerated by heat or Lewis acid catalysts. It is used extensively in organic chemistry for synthesis, including pharmaceuticals, agrochemicals, and materials. Orbital symmetry and HOMO LUMO in DA reactions. Diels-Alder reactions are thermally allowed cycloadditions that occur via a concerted suprafacial pathway, in which the DNA's HOMO, highest occupied molecular orbital, interacts with the dienophile's LUMO, lowest unoccupied molecular orbital. The reaction proceeds due to the matching symmetry of these frontier orbitals, allowing constructive overlap. Frontier molecular orbitals, FMO. The reaction is governed by the interaction between the DNA's HOMO, for 1,3-butadiene antisymmetric, and the dienophile's LUMO, for ethylene antisymmetric. Symmetry matching. For a concerted reaction to be allowed, the interacting HOMO and LUMO must have the same symmetry, both symmetric or both antisymmetric. Thermal versus photochemical. Thermal DA reactions require a pathway. Allowed. Photochemical conditions are different, as excitation changes the symmetry of the HOMO, affecting allowed pathways. HOMO-LUMO energy and reactivity. Electron donating groups, EDGs. Raising the energy of the DNA's HOMO reduces the HOMO-LUMO gap, accelerating the reaction. Electron withdrawing groups, EWGs. Lowering the energy of the dienophile's LUMO also reduces the HOMO-LUMO gap, accelerating the reaction. The reaction is generally faster when the DNA is electron-rich, and the dienophile is electron poor, thereby decreasing the energy gap between the frontier molecular orbitals. The Diels-Alder (Da) reaction is a vital tool in materials science for creating smart, reversible, and functional materials. It is extensively used to develop self-healing polymers, stimuli-responsive hydrogels, and advanced coatings due to its ability to form stable, reversible, and controllable cross-links. Key applications in materials science include self-healing polymers and coatings. The thermal reversibility of the Da reaction allows for polymers that can repair microcracks when heated, via retro-Da and rebonding, extending material lifespan. Smart hydrogels for tissue engineering. Diels-Alder cross-linked hydrogels are used in biomedical applications for drug delivery, as they are biodegradable, biocompatible, and can respond to environmental stimuli like temperature. Polymer functionalization and click chemistry. The Da reaction is used to attach specific molecules to polymer backbones, for example, using furan-malamide chemistry, enhancing properties like thermal stability, optical activity, and dielectric strength. Thermally reversible materials. This chemistry is applied to develop materials that can change properties or be recycled/reprocessed by controlling the temperature, making them efficient for sustainable engineering applications. Nanotechnology and bioconjugates, Da reactions, assist in the controlled synthesis of nanoparticles and surface modification for biomedical applications such as drug delivery systems. The applications of the Diels-Alder reactions lead to the formation of many natural product core skeletons and other motifs of bioactive compounds. Though the Diels-Alder reaction was discovered in 1928, its developments and applications are still in the focus area of research ongoing all over the world. Over the past few decades, the total synthesis of natural products has grown enormously, and the role of Diels-Alder reactions in the total synthesis is unprecedented. Diels-Alder reactions also fulfill most of the requirements for the click chemistry concept. The use of Da-click reactions in the synthesis of various macromolecular architectures, bioconjugates, and hybrid materials has made this reaction one of the most popular reactions in materials science as well.